Hello, welcome back. Last time I had a couple of pretty easy puzzles that did sequence range limiter and signal error corrector. I found out afterward that sequence range limiter was designed by our good friend Chaco. I saw the George W. there but didn't quite make the connection. Anyway, so that was cool. He sent me his own solution to this, which I haven't taken the time to type in yet. Also haven't taken the time to type in the solutions I got for this and that. I'll get to them someday, but apparently not today. So let's go on to subsequence extractor. Cycle count like that, node count like that, instruction count like that. Okay. So how are we talking? I don't know. Maybe there's some communication protocol built in. Like what? I've never heard of a tessellated intelligence system before, have you? No. We're dealing with unknowns here. Keith H. Not a name I recognize, I think. Sequences are zero terminated, as usual. Oh, right. Start index, end index, read a sequence from in.s, write subsequence between start and end, including both endpoints. Oh, this shouldn't be too hard. 0, 1, 0, 1, 0, 2, 0, 2, 0, 4, 2, 3, 0, 1, 1, 2. All right. Sure. So, start index and end index from I. All right. So you will want to how many nodes am I going to need for this? What do I need to do exactly? I'm thinking... What am I thinking? I'm thinking I'm going to want this to keep track of the start index, this to keep track of the end index, and everybody needs to keep track of how many of these have come through, don't they? Actually, maybe I can do this simpler. Okay, ideas are coming to me. Okay, so this is the start index. And then this is now going to be count. This seems pretty plausible. Okay, so I'm going to, you're going to read the start, send it over here, you're going to keep it in your buffer. While it's greater than 0, you're going to discard a value, then subtract 1, then jump here. So then in range means move up, down. No, false. Right, so you don't care about that value anymore. So now you care about this. Oh, this is going to throw me off at the zeros probably, though. There couldn't be a zero length one of these, though, because these indexes have to be valid. So no, 2 zeros in a row in my input is going to be just invalid, because these have to be actual indexes. Yeah, because it's inclusive. All right, so this is fine. I can always assume that it's a sequence of at least length 1. So this will be safe to do this unconditionally. And yeah, okay, so Jez in range. In range, move up back. So right, here's where my 0 check is going to be. Jez restart. Jez start. Oh, but... that's not right. So this is a signal. I don't know what I'm going to do in here yet. Okay, so if you're not 0, that seems reasonable enough. Am I done with... Yeah, okay, so... I'm not using your back buffer. I might actually be able to... if I can fit this... you can perhaps read the... you might be able to do basically everything here, like just with these two, if I can fit the number of instructions I need here. So you read your starting index, skipped up until it's in range. This has subtracted the start index from the end index. This is doing the wrong thing. This is doing the opposite. But I can do that, so that's fine. So yeah, now that has the length. So then I move the length to the right. Just finish. So then at some point, I don't think I'll have the instruction space for this. IR. Move left, ACK, swap. So that goes in the back buffer. Yeah, I won't have the space for this. Definitely not. That's fine. I don't need it. So undo all that. So you're going to do the filtering for the other thing. Anyway, right, so you read a 0, just finish, move back down, jump loop 2. So finish, move 0 down. No, that's not necessary. You will know when to finish, because you'll get a count from here. So this just signals to you that you need to restart. Okay. Well, I can really easily get, well... yeah, I can really easily save a node here. Well, but then that's going to make my cycles go slower. I'm so indecisive here. I shouldn't even be trying to optimize anything at all. Let's, by default, not optimize for node count, just because using more nodes makes this easier to think about and makes my cycle count go down. So anyway, you get the count. You're going to do almost exactly what this does. The difference being that this will move down and this will move nil. So you have the count. You can just do that. Subtract from the count. Keep doing this until you hit 0, at which point you... Right, this is inclusive, so I do want to do it this way. Hang on, so I want 0 and 1, so this needs to happen twice. I could just add 1. That's completely reasonable. Okay. Because otherwise I would get a count of 1 when I actually need 2 values, both 0 and 1. So this needs to happen twice. All right, so you'll get a 2, move this, change the 2 to a 1, go here, move this again, change the 1 to a 0, see this, and, well, okay, it's not in range anymore. That's what I'm going to do. Out of range. Out range. Loop 2, move up, ACK. Do you care if you've gotten a 0? No, all you do is move up nil. You don't care about finish. No, you do care about that. So you do want to move up to ACK. Jez finish, jump loop 2, that's fine. Finish, move 0 down. Okay. Is this done? The 0 didn't come through. Okay, so it's not quite done. Something is slightly wrong. What happened? So you have a 0. You have that 0. You are in range. You're negating that, so you get 1. You're adding 1, so you get 2. Great. You're moving that to the down. You get your count. Until that hits 0, you move that down. Great. You got the 74. You're still doing this. I know the problem. The 0 does not make it through to... the 0 from here doesn't make it down there. That's not the only problem, though. Yes, it is. Okay, that was all. All right, I'm done. Great. That was nice and easy. Zoom. Okay. Fairly average statistics, maybe slightly worse than it could have been, but that's fine. I know I was inefficient on instructions because I just sort of copied this from here to here. It's fine. I am quite satisfied with that. All right, signal prescaler. Ooh, multiple divisions. Maybe there's a shared memory space that these two TIS-100 units have. I don't get it. Neither do I, but here we are. Is that code? What? Smiley face. One of these people doesn't understand emoticons. Now that emoji is a thing, there's probably going to exist a generation of people sometime who don't understand emoticons as anything other than what they are now. This is how we used to do it, kids of the future. Okay. Sure. So just divide stuff. Okay, so division. I forget how I did it last time. Shouldn't be too bad, though. All right. Well, this is basically a waste of a node. So that's all obvious enough. All right. So now, how do I divide again? Divide, right. So to do division, what do the stats for this look like, just out of curiosity? Widely varying. There's a very fast way and a very slow way. Okay, so if I did it the way that I previously did division, I would be on the very slow end of that. Let me think about how I can be clever and do it better. So, I can't really do any like bit shifting here. That'd be the easiest way to do these divisions, since they're all powers of 2. If I just had a shift right operator, I'd be done already. But I don't. Is there a way to implement that with arithmetic? Well, with division, yes, but I don't have division. I only have addition and subtraction. Let's see. Yeah, it's hard to think of clever ways to do this. I mean, I'm thinking of like iterative solutions, but that's going to be silly. Yeah, because if I want to add 2 100 times here, then that's going to be very, very slow. Let me think about other ways to do division than the way I implemented it last time and see if I come up with anything great here. So, some observations I'm making about this data set. I notice that every number in the input is perfectly divisible by 8. There are no odd numbers here. There are no odd numbers here. The only odd numbers that show up are here. If I make that assumption that I can always divide perfectly, it might help me a little bit. Actually, how would that help me? So what I'm thinking is I might want to actually just break this down by binary. So I'm trying to think, I need to learn some stuff. What happens if I try to put a 4-digit number through here? It gets clamped to that. Okay, so numbers are clamped. Fascinating. All right, I'm sure that said that somewhere in the documentation. So, having some ideas, this node might not be so useful after all. So you're going to count in binary. Got some ideas here. Not sure if they're going to work, but let's just see where this goes. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so 10 times that's going to happen. So you're going to attempt to do some calculations here. I could do this the slow way. I'm not ready to give up on trying to make it a bit faster yet. I feel like doing it the slow, dumb way just isn't good enough. This might be a terrible, terrible idea. I might be optimizing too early, but I think I might be able to do something clever here. You're going to be useful. Okay, so I'm going to... Let's see here. How the heck is this going to work? Hang on, so I need to define what I'm doing a bit more fully here before I just start typing a bunch. So the idea is to break this down into bits. Determine if the 512 bit is set on this. Yeah, that's completely reasonable. Kind of. I need to do some operations down here. Wait, no. No, what am I doing? Okay, so you take this, you save that. This might look crazy, but I'm going somewhere. having some ideas. Since you can't sub one register from the other, that'll clamp to 999 though, and I don't want that. What am I trying to determine here? Whether the high bit is set, and the way to do that is actually just take this. Let's only worry about determining one bit so far. So then I just sub up. So if you are greater than or equal to 0, so if you're less than 0, then that particular bit is not set. So then what does that mean? So I mean, I guess my whole idea here was this is going to decompose the number coming in into bits somehow. Then these are going to recompose those bits. This one adding that number 4 times, this one adding it twice, this one adding it once. And then write those out to... Well, no, I mean that's a multiply by 1, 2, and 4. So I would... So I kind of don't care about those bits. Okay. But doesn't this still require me to divide? Not necessarily. Okay, I'm getting some ideas here. I might be going down a path that leads to madness, but I'm not ready to abandon it yet. All right, so decompose this incoming number into bits using these two nodes somehow. Communicate which bits are set to these nodes somehow. Have them recompose. Each one recomposes differently. Ah, and I see how I would do that. Check it out. So I would do something like so this guy would, okay, so this is divided by 2, so you would do this. Well, okay, here, there's a quicker way to do this. So you're dividing by 2. You're dividing by 4. Something seems wrong about this. Why do I already have this here? Do I care about that bit? Okay, so 60, so where's an odd number? It doesn't matter. Why does this look wrong? So this is divided by 8. I mean, I can also make this work for... oh, right, yeah, divided by 8 means this is always divisible by 8 means that I don't want this bottom one. Okay. Yeah, I could add 2 zeros here, a 1 and a 0 here, a 2 and a 1 here, a 4 and a 2 here, and then make this work for non-divisible by 8 values. But let's not do that yet. Let me assume that this observation I made about the data set will hold for all the rest, including the random one. I don't know that it will, but that pattern is consistent here. Okay, so these are my parallel, right, this is how I will recompose the bits. So the messaging from here will tell each one of these whether to add this bit or to discard it and just move it to nil. then once fully recomposed, using these different lists of values, that can very quickly do that division and send it out, and not have to do the full iteration from, add 2 50 times, or 100, however many times, 100 times to this. You know what I mean? Okay, great. So that's going to be fast if I can make it work. The question is, can I decompose the bits here? I think so. Absolutely. So bit not set. Yeah, and I don't even need to... Okay, sure. So yeah, just decompose to bits here. Let me write these. So positive value is going to mean add. Anything else is going to mean discard. Yes, this seems very reasonable. You're going to have to do, you're going to have to know how many times to do this, though. Yeah, so this whole thing works on like the number of those that are... Okay, well, let's write this for one number so far. All right, so how do I terminate there? Somehow I need to terminate. Maybe somebody should just send a message, a signal through here when this is done. Move left ACK. Sure. Right, so finish was going to be this. No, this. Something like that. Oh, by the way, signal has to be passed through here. Okay, well, I mean, that fit neatly, and I can reclaim a line if I need to. Let's go ahead and do that. Am I thinking of this right? Well, before I copy that, let me make sure I'm thinking of this the way I think I am. So I listen for a signal from you, and I pass on the signal to you. This one will not have this line. If it's positive, then I'm going to jump over here, go to my back buffer, which will start at 0, add this bit, put it back in the back buffer, then proceed from here. If it is 0 exactly, then I will discard this value and continue listening. If it is less than 0, then I'll read the back buffer, shove it down there, set it to 0, save that, and restart. Yeah, looks good to me. So this works as I want it to. Cool. So then, you need to pass some signals around. This is my signal for being done with that. Let's make this something more distinctive, just in case it matters. Okay, so the decomposer. These two can collaborate, and my message needs to come through here, which is fine. So in order to decompose, all I do is subtract this. I subtract that, and if it's less than 0, then the bit is not set. I think I need to add this back in, possibly. So I might need you to hang on to this value for a moment, because I don't think I could just... Does this fit? Ah, one short. Almost. So I can't quite fit, if I have this final signal, which I do want, can't quite fit just repeating these values from here to here. And I can't stick them into your register because that's taken up by this. However, perhaps this is the one who should store that value because you're the one who needs to do the signaling, so I think that's very reasonable. So you're the one who's going to have this decomposing value in you. Okay, yes, and the rest of this should follow pretty reasonably. So you're going to do the sub up. Well, okay, no, you're going to have to save that. Then listen to a signal? What am I even doing anymore? Move up, down. Move up, back. Move back, down. Move back, down. I think I just do that. The sub 1 was something else. The sub down was something else. That seems reasonable. Okay, so first you're going to read this. Then you're going to save it. Then you're going to loop listening for a signal. Up goes into there. There's already a loop. I feel like I'm going to run out of space in this node, but maybe not. Okay, so here your accumulator is set to this. You subtract the bit. If bit is not set, you need to add it back in. If it is set, then you need to discard that value. So if bit is set, then I move 0. No, I move a positive number to the right. If bit is not set, here, do this quicker. If bit is not set, then I move 0 to the right. Okay. Is this done? I doubt it. But I got to the end of my current train of thought. Let's just analyze this a bit. Run through it. So 1, 2, 3, 4, 5, 6, 7 bits. 1, 2, 3, 4, 5, 6, 7 bits that I check. Okay. So those all line up. So first thing that happens. Input value is going to come in here and be shuffled along there. So it's saved in this register right here. I'm using all of my nodes. That's great. And you're going to save it in your back buffer. Oh, you don't even have a back buffer. You're not using that. Okay. Great. Good. So that's not needed. So it's in this register. You are then going to read a bit from here. And if you're reading the end, then you just send that on down and go back to your loop. If you're reading the end... Right, okay. So you're going to read a signal from here. A signal. A signal? Am I reading a signal or am I reading a... Well, it could be either. If you have read this value, Then you shuffle it off to the right and go back to your loop. Okay. Anyway, so if you've gotten something that's not less than 0, you send it down twice, because I will need it 1 to 2 times. In the case that I need it 1 time, I just discard it. And then continue looping and reading those. This looks very reasonable. I think this is done, and this should work fast, right? So anyway, you subtract that from up. Problem. This doesn't decompose correctly, does it? Yeah, it totally does. Yes. Yes, this is correct. Yeah, if it is 0 or greater, then I know that that bit that I just subtracted from it is indeed set. I'm going largest to smallest. And that's the way that this works. Yeah. So if the bit is set, if I still have a positive value, then I tell this to read the bit and add it to what it accumulated. I've already verified that this does what I wanted, I think. Read over those, and I think they do what I want. And then you discard this extra value that I don't need anymore, and, oh, here we go. This is why I read that so thoroughly, because I was missing that, and I wouldn't have known what was going on. All right, so read the next one. If you've received that, then you're done. If you haven't, then you subtract, and if it's less than 0, then you add it back in, because that bit was not set, so I don't want to remove it. Yeah, so I'm stripping bits out of this as it comes in. If I've stripped a bit that's not there, then I add it back in. But I first tell you what to do. I say, discard that bit because it's not there. So yeah, you discard it. And then I put it back in, and then I jump to loop. Looks great. You're reading too many. Why? Okay, I have a control flow issue of some sort. What happened? I feel like my logic is all right, so I just have like a typo or a missing jump like this one was or something. Or maybe I have a logic flaw that I have not seen yet. So you have the 400. 512 going down here. Great. 512 going down here again. Oh, I need a third one of these. That's my problem. Okay. Right, because it listens to it once. Oh, wait. No. I do need to use my back buffer. I'm overloading the ACK here. Whoops. Oh, this is going to be a problem because I can't fit all those swaps in there, can I? All right, so that's an obvious problem. I have my signals intermingled with my actual value here. So I'm going to have to do better at that. Okay. So I should only need to swap like a couple of times, so I think this will probably fit. And I can maybe minimize this more if I really need to. Okay, so up goes into ACK. Save, so you are operating on the back buffer. Move up into ACK. JLZ fin, sub up. Yeah, problem is I'm going to need to do all these swaps. If only I could jump based on the value of your other register. Oh, check it out, I can. Hold up. I know what to do. Remember that whole JRO trick that I was trying to remember before. So you need to send... a different sort of signal here. Yeah. So I want to actually do a J row up. Yes, that sounds great. So you're going to either give me 1 if that's not less than 0, or you're going to give me 1, 2, 3, 4, 5, 6 if it is. Okay, so that should be what I need. So you don't even need to use a register for signal processing or anything. Yeah, I told myself to remember that technique. It is important. So did I phrase all this correctly? Do you know I could probably minimize this with some of the same sort of stuff? Yeah, but I'm not going to bother right now because this is the only one that really needs this strictly to work. So I'm crippling my cycle count by not doing that. But I'm not going to worry about it. Do you work? You're reading an awful lot of those without outputting anything, so no. Is 6 correct? Whoa. Move 6 down. J row up. Yeah, that's correct. Move 0 right. Wait, 0? Oh, I jumped the wrong way. You was supposed to be 9. You were supposed to be 9. Grammar. So BNS, right. I just jumped to the wrong label. Okay. Hey, there we go. My crazy idea worked. Now, next question. Do any datasets have something that's not divisible by 8? And also, does it matter? I can add more bits here, and here, if I need to. But yeah, so this runs in constant time. If I had done the traditional divide, like I had implemented it in Signal Divider, this would have been in variable time. But this will take the exact same number of cycles for every number in here. I could maybe introduce an extra optimization to bail out early if you hit 0 early, but that might end up not being worth it. So that would again be variable time. And I don't know if the savings would add up to more than the extra overhead of checking 0 every time you go through this whole thing. Because like I'm saying, if you get exactly 512 there, you only need to know about the first bits. So that would depend on the data set. Sometimes that would save and sometimes it wouldn't. Okay, so this works. Nice. I came up with something better than the naive slow solution. And my assumption did hold true. Nice! I'm at the low end of cycle count. Not all the way down, but at the low end. I think maybe that J row I was talking about over here could get it all the way down, potentially. Maybe? Although it'd be complicated because you have to propagate the signal to the right. Instruction count's very high. Node count, well, yeah, I used all of them. But I'm happy with my cycle count. That's what I was optimizing for. Okay, good. I had a great time there. Cool stuff. And yeah, I'm happy enough to be here. This is close enough to that. And I saw how I could optimize that further. Okay, so next time, if I find the time, I'll actually get the other people's programs in and take a look at... was it this one? Yeah, this one and that other one. If not, then we'll move on to Signal Averager. One or the other. All right, I'll see you then.